Proceed with the next talk of our morning session. Speaker is Torres-Perez from Vienna University of Technology. He will talk about Radio's conjecture, strong Chang's conjecture, three properties, and two cardinal square conjecture.
Okay. Thank you very much to the organizers for giving me the opportunity to give a talk. So first I'm going to give a small problem in a finite version of a more general problem. So does it work, the microphone? Yeah? Okay, thank you. So take a linear order, okay? And suppose we have a family of intervals or convex sets here. I mean, I am lifting up the intervals. So for example, this, no, and I don't know, over here. So the question is if it is possible to color this family of intervals in two colors in a way that each color is totally disjoint. No, for example, I can color this and this from a color, and they are disjoint. They don't cross. No, and well, let's ignore this for a while, and we can color this and this. No, so the green ones are disjoint and the red ones are disjoint. Okay, so but if we have a configuration, for example, like this, it is clear that we cannot color in two colors these three intervals in a way that they are separated, they are disjoint. Okay? So a necessary condition for a family to be colored in two colors, in two disjoint colors, is that at least each subfamily of three have this property. Okay? This is a necessary condition. So Rado proved that this is not only necessary, but it is sufficient. No? So we say that a family of intervals F contain L is two disjoint if F is of the form F0 union F1 such that Fe is disjoint, yeah. Or every interval, every couple of intervals is mutually disjoint. Okay, so Rado proved that F is two disjoint. This is Rado. If and only if for every subfamily F prime of size 3 is two disjoint. Okay, so actually he proved a more general version of this. So instead of putting 2 here, he proved for n. No, so it's the same definition. No, so instead of 2 disjoint, we have till f n minus 1 here, and here is n if and only if each subfamily of size n plus 1 is n disjoint. Okay, so this is a theorem. So this is valid for every n. Okay, so since we are in the workshop of what is the role of higher infinite, the next question is what happens when instead of n we use the first infinite cardinal. So Aleph 0 here and Aleph 1 here. Okay? So this is known as Radha's conjecture, and he conjectured that it is a theorem. So, so let's see what happened there. So we have Radha's conjecture. A family of intervals of a linearly ordered set is the union of countably many disjoint subfamilies, sigma disjoint, if and only if every subfamily of size Aleph 1 is sigma disjoint. Okay? So Todorsovich proved that this is consistent via a strongly compact cardinal, and however, he proved also that Radha's conjecture implies the negation of the square principle for every uncountable kappa. So it is like a large cardinal property, this Radha's conjecture. So we are going to abbreviate Radha's conjecture by RC. So Radha's conjecture has many properties, like the forcing axioms, classical forcing axioms, like PFA, for example. No? Matteo proved that PFA implies the singular cardinal hypothesis, and Radha's conjecture also proved this. It's proven that Radha's conjecture implies the singular cardinal hypothesis. Radha's conjecture is consistent with CH and the negation of CH, but it implies that it is at most Aleph 2, the continuum. Also, it is proven that Radha's conjecture implies a strong form of Chang's conjecture. So it seems that Radha's conjecture may be a consequence of Martin's maximum of PFA, but it turns out the following. No? So this is what I said. Todorsovich has shown the consistency via a strongly compact, and is consistent with CH as together with the negation of CH. However, Martin axioms implies the negation of RC, so it is incompatible with these forcing axioms. So as I have mentioned, Radha's conjecture implies that the continuum is at most Aleph 2. It implies that theta to the Aleph 0 is equal to theta. So in particular, it implies the singular cardinal hypothesis, and it proves that the failure of square and a strong form of Chang's conjecture. Also, well, there are other consequences, and Feng proved that Radha's conjecture implies the saturation of the non-stationary ideals on omega 1. So, okay. So another problem that we were interested is when a tree has an uncountable branch. No, this is so it's kind of. I mean, there are trivial counterexamples when a tree doesn't have a cofinal branch. No, take the Aleph 0, Aleph 1, Aleph n, all the cardinals here. So if you see this as a tree, it doesn't have till Aleph omega. No, it doesn't have a cofinal branch. No? So. So we can just bound the sides of the levels of the tree. So we say that a kappa Ahrenstein tree is a tree of height kappa plus with levels of cardinality kappa, but no chains of length kappa plus. No? So there is no cofinal branch. So for example, it is known that PFA proves implies that there are no Aleph 2 Ahrenstein trees. So a question was if Radha's conjecture implies something similar. We call kappa plus Ahrenstein tree special if it can be decomposed into kappa antichains. So there is a theorem by Specker. So CAH implies there is a special Aleph 2 Ahrenstein tree. So CH is a necessary condition to not to have special arrangement trees, to have special arrangement tree. So if we don't have any special arrangement tree, a necessary condition is the negation of CH. So we prove with Estevo that this condition is not only necessary but sufficient. So we prove that under RC, CH is equivalent to there is a special Aleph2 arrangement tree. So both ways. So, but actually we have a little stronger result here. So strong conjecture is the following statement, and this strong chance conjecture is a consequence also of Rao's conjecture. So this is going to be relevant because many of the following results are going to be consequences only of this chance conjecture. No? So we say that for chance conjecture, this strong version of chance conjecture holds if for every regular cardinal kappa there are arbitrarily large lambda such that for every countable model and every subset of kappa of size omega 1, we can extend this model such that the countable ordinals are preserved, and we can find a B also of size omega 1 in M, in this extension in M star, such that it is contained, it extends A, sorry. Here is missing the, here is, it should be written somewhere that B contains A. So, so we prove that under chance conjecture, these are equivalent. No? So, okay, so is it? But we are talking only about special arrangement trees, Aleph2 arrangement trees. So, can we have not arrangement trees at all? I mean, can we kill all the arrangement trees, not only the special ones, but all of them? So, with Lützen, well, this is the tree property. A regular cardinal kappa has the tree property, and we denote it by TP kappa if for every tree of height kappa with levels of size less than kappa has a cofinal branch. So, for example, we know that Aleph 0 has the three properties. This is the Koenig's lemma. Aleph 1 does not have the three properties, so there is an arrangement tree of height Aleph 1 that doesn't have cofinal branches. And a tree of height omega 2 with levels of size at most omega has a cofinal branch. So what about trees of height omega 2 but with size of levels of size at most omega 1? So we have said that CH implies there is a special Aleph2 arrangement trees, and PFA implies the tree property for omega 2. Okay, so it is consistent to have either of them, the negation or the TP omega 2 holds. So yes, so we ask if Rao's conjecture was enough to kill all the Aleph2 arrangement trees, and with Lützen Wu, we proved that the strong chance conjecture plus the negation of CH does imply TP omega 2. So it has a tree property. So it was enough, the negation of CH. No, again, no, it was a necessary condition, the negation of CH, but it is also sufficient to prove that TP that omega has omega 2 has a tree property. So how about we have seen the special tree property, the tree property, and how about stronger versions? No, so we have this definition of it was popularized by Weiss, but it was written first, I think, by Yeh. So let kappa greater than omega 1 be a regular cardinal, and lambda greater or equal than kappa. So we have a collection of sets such that there are functions there are functions, binary functions of which domains are the subset of size less than lambda of kappa. Okay, so for every a, this is the level. This is the level. So each level is of size lambda, and and it is downward closed. No, so we have two functions. We have a function in one level. Then the restriction to a subset is also in this kind of tree. No, this is not a tree really, but this collection of families. So we say that this collection of families is a kappa lambda tree, and Fa is the level A for A in subsets of size less than lambda. So again, we furnish F with the following order: if two functions are comparable, if one is restricted to the other, are equal to the domain of the other. Sorry. So in general, this is not a tree order. And a cofinal branch F is a function from kappa to 2 such that it passes through every single level. Okay. So we say that lambda has the strong tree property if for every kappa lambda tree has a cofinal branch for every kappa greater or equal than lambda. Okay. So Bayes proved that PFA implies Aleph 2 has a strong tree property. Okay, so this is, I mean, this is more or less analogous to weakly compact for the tree property, no? Because a cardinal kappa has a tree property if and only if it is inaccessible and weakly compact, no? And a cardinal has the strong tree property if and only if it is inaccessible and it is strongly compact. Okay, so and Sakai and Velichkovich prove that Chang's conjecture and MA restricted to Cohen together imply that Aleph 2 has a strong tree property. But as you remember, Martin's axiom is not compatible with Rao's conjecture. No, so we didn't know if Rao's conjecture implied also that Aleph 2 has the strong tree property. So with Liu Zhengwu, we proved that it is again also enough to have non-CH together with Chang's conjecture to imply that Aleph 2 has the strong tree property. So as a corollary, Rao's conjecture also implies that Aleph 2 has the strong tree property. Okay. So as you remember, we proved that, well, now we go back to the squares. Well, I don't know if I have enough time, but I suppose that most of you know the definition of a two version of a square. The only difference with the normal square is that we allowed lambda many guesses here. So and yes, this is the kappa lambda square. So square kappa kappa is a consequence of CH actually, no, of the general CH, and it is well known that square kappa kappa is equivalent to the existence of a special kappa plus Arnstein tree. So we have the following, no, with Estevo we have proved actually that under CC star square omega 1 and R and CH are equivalent. So what about other versions of these two cardinal squares? Well, actually, we assume the whole RC, and we have these results that we have the negation of kappa less than kappa for any countable cardinal kappa. The second result is the one I have already mentioned. The negation of kappa kappa for every singular cardinal of cofinality omega. No? There were some cases that were missed in these results. No? For example, we are going to compare it with some results of Cummings, Magidor, and Baumgartner, assuming MM. So assuming MM, we have the following, that we have the negation of kappa less than cofinality of kappa whenever kappa is uncountable an uncountable cardinal. This result is by Baumgartner, that the negation of omega 1 squared, and also the negation of kappa kappa whenever kappa is an uncountable cardinal of cofinality omega. No? So this is what we had with Esteban and Rao's conjecture, and whenever kappa is uncountable, they proved more. No? So whenever kappa is uncountable cardinal of cofinality omega 1, they prove that the negation of square kappa less than kappa holds, and even more. No? So if there is a super compact cardinal, then there is a class forcing extension where MM holds. And we have that it holds also kappa cofinality of kappa for every cardinal with cofinality kappa greater than omega 1. And also that we have square kappa kappa holds for every singular cardinal kappa of cofinality omega 1. Well, I mean, there are many cases, but the general idea is that they covered the whole cases. Cummings and Magidor and Baumgartner. And actually, a very nice work by Sakai. He did exactly the same for Chang's conjecture and Rado's conjecture. No, it's he proved exactly the same. Well, here it is necessary just the negation of CH. No, but he proved that it is enough Chang's conjecture to have similar results. Are exactly the same results of Cummings and Magidor. So it is, I mean, it is going to be appeared in a common paper, but these results are of Hiroshi Sakai. However, most of the proofs for square principles are based in this other principle. Fix a regular cardinal theta. The principle square theta holds if there is a sequence of subsets of theta such that for every theta in the limit points of theta, delta in the limit points of theta, again, C delta is a closed and unbounded subset of delta. And if gamma is in the limit points, we have this coherence property. But the third property is that there is no closed unbounded set of theta such that for every gamma in the limit points of C, C intersection gamma is C gamma. So it is said that there is no club trivializing the sequence. So actually, we have that square kappa plus implies square kappa plus with rounded brackets. And well, actually, Todorsevich proved that the negation of so it is to prove the negation of this is stronger of to prove the negation of this. So actually, Todorsevich proved that the negation of this square holds on their Rado's conjecture. And Sakai and Velichkovich prove also that Chang's conjecture is enough to prove the negation of this type of a square. So how about a two-cardinal version of this? We are going to say that a sequence, again, we are going to allow, in this case, less than lambda guesses, sequence whenever the size of the family is less than lambda, and for each limit, for each member of the family is a closed bounded set of delta. And it has this coherence property. You know, if zeta is in Z delta and gamma is a limit point of C, then zeta intersection gamma belongs to C gamma. But we have not said that it is the square less than lambda delta principle, no? Because I don't know. I mean, we had some problems to prove things. So we said that an ascent path theta of the sequence is a sequence of non-empty subsets of theta such that whenever xi is less than eta, every ordinal xi is more than every ordinal of a eta, sorry, and there is a connection between them. No, so there is somebody here and somebody here, and that they are connected by a member of that. No, so they are in a certain way connected. So we have proved with So we recall that the existence of an ancient theta path of sets of cardinal. Okay, so the triviality in this sense is when the traditional one is when the cardinality of these ascent paths is just 1. No, we have a clause trivializing the sequence. So this is like a natural weakening of this notion. So okay, so I will just skip this. So we have proved with Estevo that on the Rados conjecture, we have also that for every sequence of this form, every sequence of this form has an ascent path of countable subset of theta whenever this set contains a closed and unbounded subset of size less than theta. No? So this is in this direction to see if this other version of the squares principles we can have like also nice results, no? Like we had before. And recently we proved with Lutzen also that this sequence is also trivial. It means that under Chang's conjecture, the negation of square omega theta holds for every regular cardinal and theta greater or equal than omega 2. And this is what we have till now. So we hope that somebody can find other relationships with this Chang's conjecture and this new kind of square principles. That's everything that I want to say. Thank you.
Well then, thanks again.